because of that, because of the fact that these two things each equal the same constant, we can now solve this flow completely. So we're trying to solve for flow between these two plates. We've got x equals, x in that direction, y in this direction. We've put the center of the coordinates in the midplane of the flow. So this is the flow coming this way. And we've got that, y equals 0 is right in the center of the channel, and h over 2 is the top of the channel. So and minus h over 2 would be the bottom of the channel in the y direction. So we're going to go ahead and solve this for the velocity. So I'm going to take this, I'm going to say, well, mu d squared u dy squared is equal to some constant, which I'm calling g. So, all right, I can easily integrate that. So I have d by dy of du dy is equal to g over mu. Now I'm going to multiply both sides by dy. I have d of du dy on the left, and on the right I have g over mu dy. I take the integral of both sides. The integral of d du dy is just du dy, because the integral of d anything in this parentheses is just whatever that thing is. So the left-hand side is simply du dy. And the right-hand side, of course, is g and mu are constants, so g mu y, and then, of course, I have to add a constant of integration, c1. Now I can do the integral. I can integrate again. So I have du dy. I move that dy over to the other side. Du is equal to g over mu y plus c1 all times dy, and I integrate both sides again. The left side, of course, is just now u. The right-hand side is going to be g over mu y squared over 2 plus c1y plus some new constant, c2, constant of integration. So that's my general solution. Now I have to apply my boundary conditions. Boundary conditions. So my first condition I'm going to apply is what's called a symmetry condition. So symmetry condition says that du dy equals 0 at y equals 0. Because in the middle of this channel, I don't exactly know what the shape of this velocity profile is, but there's no reason to think it's not symmetric top and bottom. So right here at this, whatever this is, the top is going to be the same as the bottom. This channel is completely symmetric. So I can say that one condition then is that the du dy will be 0 at y equals 0. And that's an easy condition to apply. So du dy is easy to see. Du dy from here, you can just actually look back. We had it a second ago anyway. Is equal to g over mu y plus c1. So we set that equal to 0. So 0 on the left equals g over mu, and that's y equals 0. So there's a 0 in here plus c1. So that term goes away, and you have c1 is equal to 0. Very important now that you update your solution. So that's our c1. We plug that back in up here and update our solution. So we have a new u term. Our u expression is u as a function of y is equal to g over 2 mu times y squared plus c1 is 0, so just plus c2. So that's our new expression for our conclusion for u. Now we apply our second boundary condition. U equals 0 at y equals h over 2. That's where the wall is, right? So we've got our no slip condition. At this point, y equals h over 2. That's where the velocity has to go to 0 because of the no slip condition. So we plug those things in. We have u at y equals h over 2 is equal to g over 2 mu times h over 2 squared plus c2. So that means that I set this left-hand side equal to 0 because that's what the velocity has to be at the wall. So 0 on the left is equal to g over 2 mu h squared over 4 plus c2. And you crunch that around and you get c2 is equal to minus g h squared over 8 mu. That's my C2. Now I have to plug that in and update my solution. So I have u as a function of y is equal to g over 2 mu y squared minus g h squared over 8 mu. But I'm going to clean that up a little bit, so my final form will be prettier. U as a function of y is going to be equal to g over 2 mu times y squared minus h squared over 4. So you get, as we talked about earlier in the class, when you have flow between parallel plates, you get a parabolic velocity distribution. And this is the velocity distribution that you get. But at the moment, I don't know what g is. It's a constant, but I haven't determined what it is. So this gives us the shape, but it doesn't give us the magnitude yet of the velocity.